Okay, now let's see how we can implement a queue. As I mentioned earlier in the previous video, we can have different implementations for queue. We can implement it using arrays, we can implement it using linked list. Now let's see how we can implement it using what we call linear array. So here I have a fixed size array, static array, assuming that the size of the array is 5. We want to see how we can implement a queue. So as mentioned earlier, you can think of a queue as a corridor that has two open ends. One is the front, one is the rear or back, and the data is going to be entered from the back and it's going to be removed from the front. Okay, so let's first see how we can insert the data, how we can enqueue. Okay, so now I'm just gonna work on enqueuing data, and I'm gonna write a pseudocode for that. Enqueue, yeah, okay. So I'm gonna write a pseudocode for that. So let's say that we wanna enqueue number x. So let's say that x is 10, and we wanna insert 10 to the queue. We want to enqueue it to the queue. Okay, so if x is 10, so initially we need to have two variables, one representing front, one representing rear. What we keep in these values is going to be the index of the front and rear of the queue, because we know the size of the array, right? But front and rear basically tell us where the start of the queue and where the end of the queue are, right? We're not going to be using the whole array for the queue. Our queue might be starting from here, so the front might be here, the rear might be here, the front might be here, the rear might be here, the front might be here, the rear might be here. So we have to consider all these scenarios, or like any other scenario that you might have. So what we do, we initialize both front and rear with number -1, right? So when both front and rear are -1, it means that our queue is empty. Okay, so in this case, our queue is empty, right? And when we enqueue, so at this point, like here, like you can think of that front and rear are both -1. It means that our queue is empty. When we enqueue the first number, so what we want to do, we want to insert 10 here. At this point, this is going to be both front and rear of the queue. So we want to increment front and rear both to 0. We want to increment them by 0. So this is the first like one thing that we have to write here. So if front is equal to -1 and rear is equal -1, this is gonna mean that our array, our queue is empty, right? So what we want to do, we want to initialize at this point. We want to initialize both front and rear. Not initialize. We want to change the value of both front and rear to 0. Front and rear both going to be equal to 0. I'm writing a pseudocode. This is not a C++ code. And I just want to emphasize this, that this is one way of implementing queue using linear array. You might see, or you might hear different implementations, as long as it follows all the rules of the queue, that's going to be fine. Okay. The next number that we want to enqueue, let's say it's going to be number 20. Okay, in this case, 20 should go here. So this is going to be our front of the queue. This is going to be the rear of the queue. Okay, and like before I mentioned this number, at this point, if like after incrementing front and rear both to 0, we want to say that A of rear is going to be equal to X. Okay. So at this point, now, so we incremented both front and rear to 0. A of rear is going to be X. So it means A0 becomes X, which is 10. Now the next number, which is 20, it should go here. You remember we inserted from the rear, so it should go here. Do we have to increment the front? At this point, this is the front, this is the rear. And front is 0, rear is 0. Do we have to increment front? No, because our front didn't change, right? So the only time that for enqueuing we have to change the front is when our queue is empty and we are going to insert the first number, right? That was the case. If that is not the case, what do we have to do? We only have to increment the rear. So rear plus plus at this point. So rear becomes 1, and then we insert X into A1, or I should call it array, as I named this ARR. Okay, and I keep doing that. Let's say the next number is 30. Is front -1 and rear -1? No. And to be perfectly clear with you, this condition, you can just like reduce it to this one. Doesn't have to have both of them if you implement it right. Okay, because if front is -1 for the linear array implementation, it means that our array, our queue is empty, right? We don't have to check the rear as well. So just wanted to tell you that too. So at this point, this condition is not true. So we're gonna increment rear. So this becomes 2. We insert X, which is 30, into ARR2. Next number, let's say 40. Let's say 10, 20, 30, 40. Same thing. This is not true. So we're going to go here. This becomes 3. And we're going to insert 40 here. And finally, let's say like the last number, 50. And again, front and rear, none of them is equal to -1. This condition is false. So we're going to increment rear. And we're going to insert 50 here. Okay. Is our code complete? Are we done? We are not actually done. Why? Because what's going to happen if we want to increment another number? Sorry, if we want to enqueue another number, let's say number 60. It's going to come here. It says that front is not -1, so this is not true. It wants to increment rear to 5, and it wants to insert X into ARR5, right? So as mentioned in the previous video, whenever we want to enqueue, we have to make sure that what is the precondition for enqueuing? We have to make sure that our queue is not full. Otherwise, we're going to have overflow, right? So what should we do before doing any of these? We have to check if our queue is not full. In the linear array implementation, what should be the condition to check if array or if the queue is full or not? See, like here at this point, our queue is full. Does it depend on the front? No. It only checks the rear, right? So like what I have to write here, if rear is equal size minus 1, right? At this point, this means that our queue is full. So this is a void function. So what I can do is basically print a message. If you want, you can write a cout something and just return, or if you want, you can throw an exception. Okay, so now my enqueue or our enqueue function is complete. We check if the queue is full. If it is full, then we can't do anything. We can't enqueue any other number. We check if our queue is empty. The only reason that we have to do this is because we want to make sure that our front is changed correctly, right? That's the only condition. That's the only time that our front is going to change, when we enqueue, because you remember we only enqueue from the rear, right? So that's like most of the time is rear the variable that's going to change. Front is only going to change when our queue is empty and we're going to insert or push or enqueue the first number, right? At this point, we change both front and rear. In other cases, we only have to increment rear, okay? And what I do after all these, like, so these are like all part of the function. So at this point, after changing the front and rear, and we're gonna insert x in the correct index of the array. Okay, so this is like one of the functions that we have to write to implement queue using linear array. What is the other function that we have to write? The other function that we have to write is dequeue. Okay, so for dequeuing, we basically first we have to check. You remember that again, the precondition for dequeuing is that we want to remove data from the queue, right? So there should be some data in the queue to be removed, right? That's the precondition. If our queue is empty, we cannot dequeue, right? In what case our queue is going to be empty? Once both front and rear are equal to -1, or as I mentioned earlier, even this one is going to be sufficient, but I'm just going to write both of them to just be like, write the general case. If that's the case, we can't do anything, right? There's no data to be dequeued from the queue, so we just return or like print a message. This is not complete code, right? You can print a message, the queue is empty. You can either throw an exception or you can return. And that's basically checking the precondition here, okay? And then in this case, I'm just gonna do it step by step. If I want to dequeue, you remember that dequeuing happens from the front. Okay, so what I only need to do is changing the front, right? Right now, our queue starts from this index to this index, right? If I say front plus plus, my front is gonna change to 1, right? That means that my queue is only gonna be from here to here. I don't care what's in this one. I don't have to change this one, right? Because right? It's going to be overwritten anyways, right? So we're not going to use it because we're only going to be using the Q from the front to rear, right? So at this point, this is going to be DQ'd, right? This is removed from the Q. Again, I want to DQ another one. This is going to happen. 20 is going to come out. Front plus plus. I want to DQ another one. So in this case, this is my Q going from front to the back, right? And 30 is out of the Q. Another one, DQ operation. 4 and 4. Okay. So look at this case. At this case, I want to, so like right now I only have 50 in the Q. If this is the last number that I want to DQ, what's going to happen at this point? After this operation, our Q will become empty, right? If I remove 50, our Q is going to become empty, right? So if the Q becomes empty, what should be the front and rear of the Q? Think about it. So at this point, when front and rear are equal, when you want to remove the last number from your Q, at this point, after this DQing operation, both front and rear should become -1 so that we know that our Q is empty. So we have to check this. If front is equal rear, this means that we only have one number in the Q and we are doing the DQing. We are DQing the last number in the Q. So after this, our front and rear will be both equal to -1, right? So if this condition is true, this is the only time that we have to change the rear. We also have to reset front to -1. We can't increment it anymore. We don't want a front to become 5 because it's going to be out of bound, right? So if front is equal rear, make both of them equal to 1, else do the front plus plus. Okay, so this is checking if the Q is empty or not. This is checking the last DQ, that's legal DQ operation, and otherwise we're just gonna have only incrementing the front. And like when we do this, the last number is DQ'd. Okay, if you want to display the Q, you only have to write a loop that goes from the front to the rear and just display the Q. If you want to return the front, if you want to write the front function, you would just like have to return the A front. If you want to write the rear or back of the Q, you only have to return A or array rear or array back. You just have to make sure that our arrays our Q is not empty though, right? So you always have to check that. If our Q is empty, like there's nothing to return. Okay. Now, what is the problem with the linear array implementation of Q? What happens if I only do let's say like our Q is like this, 10, 20, 30, 40, 50. So like our front is 0 and so like this is what we have, 10, 20, 30, 40, and 50. Let's say that we do 2 DQ operations. So if we do two DQ operations, the first one, it's gonna remove 10. It's gonna actually stay, but it's not gonna be part of the queue. So 10 is removed from the queue, front becomes 1. Another DQ, front becomes 2. 20 is out of the queue. This is out of the queue. And this is what we have. So this is the queue that we have. Okay. What if at this point I want to NQ another number into the queue? Can I do it? No, I can't. Because you remember that now rear is equal the size minus 1. There is no more room here to NQ another number, let's 60. But am I using my array efficiently, memory-wise? No, I'm not, because I actually have 2 empty spots here. Why shouldn't I be able to NQ, right? Although I don't have any more spaces here, right? But I should be able to like take advantage of these 2 empty memory spaces. I can't do that, right? So that's the problem with the linear array. It's not very memory efficient, okay? So that's why we want to see how we can implement circular array. That's going to be the topic I'm going to cover next. One thing I want to emphasize here, you see that for both NQ and DQ operations, the complexity, the time complexity is big O notation 1, similar to what we saw for the stacks, right? We only have one operation. Like you don't see any loops here, do you? No. The same thing for NQ, right? So that's actually why like we have to have 2 variables to just keep track of both front and rear, right? That's why like this is going to be big O notation 1, okay? So it's a constant time for NQing, DQing any number into or out of the queue. Okay, so the next video I'm gonna show you how to do circular queue. Okay, so now we saw what the problem was with the linear array. We saw that if we have a situation like this, that we have some empty memory spaces in the beginning of the array, but the rear part of the array is full. We can't NQ any more numbers, though we have like empty memory spaces. Now we want to see how we can solve this problem using the concept of circular array. So in the linear array, our array starts from index 0, it goes all the way to size minus 1. In the circular array, we basically want to be able to go back to the beginning of the array and check if there is empty space. We want to NQ here, and then this is going to be our rear. Our front is going to start from here, but our rear is going to be here. Okay, so let's do it step by step. At this point, our front is equal to 2 and our rear is equal to 4, and I want to NQ another number. This is the previous NQ function or pseudocode that we had for linear array. Okay, so what we did, we incremented rear, right? Whenever we wanted to NQ, right? But if I do that, my rear is going to become 5. I don't want it to be 5 because there's no space here in the array at index 5. This is out of bound of the array. So how can we solve this, right? If you remember about the remainder operation, right? So whenever you exhaust the array, if you want to insert one more here, it's as if you're dividing that number by 5 and then you have the remainder, right? So at this point, the only thing we have to do is take advantage of the remainder operation. Okay, so we check that our array is not full, right? You're here, like we check that the array is not full. We have to change this one later. I'm going to show you that this is not going to be the correct condition for circular array implementation. But here we check that array is not full. It's not full. Okay. If it's not full, it means like that we have empty spots here. Okay. So then I can just say rear is equal to, instead of incrementing rear to 5, so we're going to say rear is equal to rear plus 1, which is going to be 5, mod size. What is size? Size of the array, 5. So rear becomes 0. So at this point, our rear is going to be smaller than our front. That is okay, because we have like a circular concept here. Now we're going to insert or NQ60 here. Okay. Remember that this one is only going to be like important, or like it's gonna have like some meaningful values. It's gonna when like you get to the end of it. Otherwise it doesn't matter, right? If we had this case, if we had like front and rear were like this was front 30 and our rear was 40. If that was the case, this is going to be the same as rear plus plus, because once you increment 3, it's going to be 4. If you divide a number by a bigger number, the remainder it's going to be the same number, right? So it's going to be 4. So this is always going to be rear plus plus, unless you have exhausted the array, like unless you have reached the end of the array. Okay, so at this point, when we got here, our rear becomes 0. Okay, so let's see another case. We want to NQ another number, right? We want to NQ another number, let's say number 70. Okay, so we have to check if the array is not full. Okay, we're going to see that this is not going to be a correct condition for circular array. We check the array is not full. If it's not full, it means that we have empty spaces. We also check that array, I should have said queue. We check that the queue is not empty, because if queue is empty, we have to change both front and rear, not just the rear. And we have to reset both of them to 0. This is the first number that we're going to enter. If not, rear is going to be rear plus 1 divided by size. Take the remainder. Let's look at it. Now rear is 0. 0 plus 1, it's going to be 1. 1 modular 5, it's going to be the same as 1. So in this case, this is going to be exactly the same as rear plus plus. The only time that these two are not going to be the same is when you reach the end of the array. So at this point, we have reached the, we took advantage of the empty memory spaces. Our rear becomes 2. Oh, sorry, 1. Sorry, it was 0, now becomes 1. Okay, now, okay, let's see if this condition is correct or not. I want to NQ another number. Let's look at our array. What do you think? Can I NQ another number? No, I can't. My array is full. But look at this condition. Is rear equal to size minus 1? No, it's not. So I can't keep this condition to check if my queue is full or not. I have to change it. Okay, how can I make this correct? I can make it correct by saying that if rear plus 1, if you look at it, again, I'm going to do it step by step. This is not going to be the correct condition. If in this case, you can see that rear is going to be 1 before the front. So at this point, this is going to be fixing the problem, right? So this is going to fix the problem. But this is not a permanent solution. This is not the correct solution. Let's look at, again, let's start from an empty Q and see if this condition would work correctly. So our front and rear are both -1. We're going to NQ 10. So both front and rear become 0. We're going to NQ 20. Rear becomes 1. Insert the 20. 30. Rear becomes 2. This is front. This is rear. Like NQ another one. Rear 3 and 40. NQ another one. Rear 4. NQ 50. Now the array is full. Is this condition checking if the array is full or not? Is rear plus 1 equal to front? No, it's not. Okay, so how can I change it? Look at it. What is rear plus 1? It's going to be 5, right? Is it equal to front? No, it's not. But what if I do it like this? If rear plus 1 mod size is equal front, because you see that like we're gonna circulate, right? This circulation, it's as if we are dividing the index by 5 and taking the remainder. Okay, so we have incremented and divided by 5, take the remainder. So that's gonna fix the problem. At this point, rear plus 1, it's gonna be 5. Modular size, which is also 5, it's gonna be equal to 0. So this is gonna check if the Q is full or not. Now this is gonna be the correct pseudocode for NQing for a circular array. We check if our Q is full, right? This is gonna be the correct condition for like all the scenarios that we saw. This is gonna check if this is the first number that we wanna NQ into the array, and this is gonna be otherwise, right? If our Q is not full, right, and if this is not the first number that we wanna enter, we're just gonna change the rear, right? So we wanna increment the rear, right? But when we reach the end of the array, we want to be able to circulate back to the beginning of the array. How do we do that? By incrementing the rear, dividing it by size, and changing the rear to the remainder of this operation, and then do the insertion. So this is going to take care of the NQ operation for the circular array implementation. Now let's look at the other one. The other operation that we have to write for a Q implementation, DQ. Okay. So let's go back to the example that we had. Let's say that this was the case. Let's say that my rear is 1 and my front is 2. Okay, so it means that this is the rear, this is the front. Our Q starts from here, 30, 40, 50, 10, 20, right? Let's see if this DQ function needs to be changed. This DQ pseudocode needs to be changed. So what do we have to first do when we want to DQ? First, we have to check if our Q is empty or not. if it is empty, this is going to be the condition, because we always make sure to initialize front and rear to -1, right? So that's going to be correct. We don't need to change this part. Okay. Now, the next thing that we checked is if front is equal to rear, right? If front is equal to rear, that means that we only have one data left in the queue, and we are dequeuing the last data, right? So after this dequeue operation, our queue is going to be empty. So what do we have to do? We have to initialize both front and rear to -1. So this was correct. This is also correct. You don't have to change these two conditions. How about this one? Okay. How about this one? So let's say that I want to dequeue here. I want to dequeue at this point. Okay. So what should be the number that's going to be dequeued? Is it going to be 10? No, because we always dequeue from the front. So it's going to dequeue this one. Front becomes 3. So I'm just going to remove this so that you know that this has been dequeued, and front is going to be now here. So that's correct so far. Let's do another dequeue operation. So front becomes 4. 4D is also out of the queue. Okay, let's do another dequeue operation. It says front plus plus, right? Should I change this to 5? We don't have any, this is out of bound. We don't have any index 5 in this array. We want to be able to circulate back so that the next number we dequeue should be this one. Right? So can you guess what we have to do here? It's very similar to this one. So we just have to say front is equal to front plus 1 modular size. If that's the case, now front becomes 0. Right, so front is going to be here. Okay, now let's look at it. Let's see if this condition works fine when front is before the rear. Right, so we want to dequeue another one. So front should become 1. Does it become 1? Yes, because 0 plus 1 is 1. 1 modular size, it's going to be 1. Right, so this is going to be removed. This is going to be front. Again, we get to this point. Is front and rear equal? Yes, they are equal. So we want to make both front and rear -1. This number is also out of the queue. Our queue is empty. Okay, so that is the circular array implementation of queue. It's more memory efficient than the linear array implementation. Okay. One thing I want you guys to practice is write a display function that would display all the numbers in the queue. Okay, so if that's the case, you just like remember that we have to write a loop, right? We have to write a loop to go from the front of the array to the rear of the array, and we print like all the elements of the array, right? But if that's the case, you have to be careful like how you write that loop, because in a circular array we can have front before the rear, but we can also have rear before the front. Okay, so we're not like, if you're writing the display function, it's not going to be just writing a simple loop going from front to rear, right? Because sometimes we might have, sorry for the mess, sometimes you might have this case, or like this case. So you have to start from the front, right? When you get to the end of the array, you would need to have another loop that goes from the beginning array to the rear. Okay, so practice with writing a display function for the circular array implementation of Q. Okay, next we're gonna see how we can implement Q using linked list. So let's look at how we can implement queues using linked list. So again, I'm just going to reiterate that if you have a queue, you should have two open ends. One end that we do the removal from, one end that we do the insertion from. So unlike the stacks that we were pushing and popping from the same end, we now have to have two ends in the linked list. One end that we do the removal from, which we call the front, and the other end that we're gonna have the insertion or pushing into the queue from. So let's see that if we have this queue so far, 10, 20, 30, 10, 20, 30, and this is the front. This is like basically the head pointer, which is also like the front of the queue. If I want to enqueue another number, let's say like if I want to enqueue 40 here, can I do it through the same pointer? Or do I need another pointer? If I want to do another enqueue through the same pointer, I have to go through all these nodes. I have to traverse through all these nodes and do another enqueuing here. So this is not going to be in the big O notation 1. This is not going to take a constant time. As we have more nodes, it's going to take us longer and longer to enqueue. So this shows that in the linked list implementation, we also need to have another pointer, which is going to be pointing to the back or rear of the queue, which is going to be the tail of the linked lists. So this is what we are going to have. So if this is our queue, we always have two pointers, one pointing to the front, one pointing to the rear. That's going to be pointing to the head of the linked list and one pointing to the tail of the linked list. This is unlike the stacks that we only had one pointer. Okay, so you can think of this linked list implementation like corresponding to the array implementation. In the array implementation, we had two variables, right? We had front and back, right? Here we also have like two pointers this time, front and back, or front or rear. When we want to insert or enqueue another element into the queue, we're going to do it at the end, at the tail of the linked list. And when we want to remove data, we're going to do it from the front. So let's now look at the enqueue part. So let's actually do this. Now like we want to enqueue another number here. So, and this is what we have here so far. And this is the back pointer, back or rear, you can name it whatever you want. Okay, so what should we do? We want to enqueue another number. So first of all, we need to have another node. So let's allocate another node. Okay, so this is just the allocation. So let's just do that. So this is temporary pointing here. Okay, so that's what we have. So this is the node that we want to enqueue into the linked list, and we wanted the data part to be x. So let's do that. T arrow data is equal to x. So let's say 40, gonna go here. And the pointer part of the node, which is t arrow next, it's gonna be equal to, let's initialize it with null pointer. Null pointer or null, almost the same. Null pointer is better because that's only specific to pointers. So this is gonna be null. Because now this is gonna be the tail of the linked list, right? So that's why we initialize the pointer part to null. Okay, so again, I'm gonna do this step by step. Let's see what we have to do here. What we want to do is basically making this one the back of the linked list, right? So what we have to do is basically saying that this pointer, we want it to point to this one. So I'm gonna write it here. Let's see if you guys can see the whole thing. Yeah. So I'm gonna say back arrow next is equal to, what should I write here? If I want to make this pointer point to this node, I want this pointer to be pointing to the same place that this pointer is pointing to. So back arrow next is equal to t. This is gonna go like this. And then this is not the back of the linked list anymore, right? So the back of the queue is gonna be this one. So how can I do that? I'm gonna write back is equal to t. That's it, right? So now this node is the tail of the linked list. This is the back of our queue. Would this be okay? Do I need to change the front at all? I didn't need to change the front at all in this case, right? So similar to the way that we implemented the queue using arrays, you see that like when you want to enqueue, most of the time we only need to change the back. What was the case that we also needed to change the front? If our queue is empty, what we have two null pointers. Both front and back are gonna be null, right? That's the initial value of the front and back pointers, right? If that's the case, when you wanna enqueue the first node, you have to make both front and back point to the same thing. Okay, so this code is not complete. I have to do a check. If front is equal null or null pointer and back is equal null. Okay, again, even only this one, if you implement this correctly, even this condition should be enough. Then we just have to say front is equal to back is equal to the t. We just want to point both front and back to where this temporary pointer is pointing to. Else do this part. Okay, so if our queue is empty, we make both front and back point to the newly allocated node. If not, we just have to make the previously tail of the linked list point to the newly allocated node and change the back of the linked list. You remember that we mentioned that whenever we want to enqueue, we have to check if our queue is full or not. Do we have to do it here for the linked list? We don't have to do it for the linked list, because for the linked list, we don't have a fixed size. We allocate as we need, right? We enqueue and we allocate as we need. The only part that might cause us an exception is this part. If the heap is full, if we don't have any new memory, if we don't have enough memory, then this is gonna throw an exception for bad allocation. But our queue is never gonna be full because we just like allocate as we need. Okay, so this was about the enqueue part. Now let's see what we have to do for dequeue. Okay, so for dequeue, in this case, when you want to dequeue, first of all, we have to check that our linked list is, or our queue is empty or not, right? So how can we check that? If front is equal null, this is just going to be sufficient, but for to be general, like I'm just going to write the whole thing. If back is also equal to null, then return, or throw an exception, or like print a message and do whatever is needed here. Okay, in the case that we have a linked list like this, okay, let's see what we needs to be done. Again, we're gonna do it step by step to realize why each part is needed. So we wanna remove data from the front. Okay, so what I just need to do is basically make the front point to this node. Okay, so what I need to do is just basically saying front is equal to front arrow next. This is gonna remove this link and make this pointer point to this one. Now, is this okay? Yeah, so my front changed. This is out of the queue, but what about this memory space? This is dynamic memory, so we have to deallocate it. Do I have any pointer pointing to it anymore? No, I don't. Okay, so this is gonna cause memory leak. So let's fix that problem first. What we need to do is first maybe have a temporary pointer pointing to the front. So let's call this one T. Make, if this is the case, if this is the front, T is gonna also point to the front. Now we do this, right? So this is gonna point to the new front of the queue, and now we can delete T. Okay. So that's the thing that we need to do most of the time. Now, again, we are only like changing the front, right? When we are dequeuing, when we are removing data, popping the data out of the queue, we are only changing the front. Now, do we ever need to change the back? What if we have a case like this? What if we only have one node in the linked list left? If we want to dequeue, what's gonna happen? Well, like the queue is gonna be empty, right? So similar to the case that we implemented the queue for array, we have to check if this is the last data that we wanna pop out of the linked list or out of the queue. We want to dequeue out of the queue. So if front and back are both of them pointing to the same node, it means that this is the last data that we want to dequeue. So in that case, we're gonna say that what's gonna happen if we pop this, if we want to dequeue this, what's gonna happen? The queue becomes empty. So we have to initialize both front and back. We have to change the value of front and back both to what? To null. I'm just gonna write null pointer this time. Okay? Else we do this part, right? So this is to check if empty. This is to check if this is the last element. And this is otherwise. Okay, so that's how we can implement queues using linked list. To do displaying the whole linked list, you just have to traverse through all the linked list. If you want to do is empty, this is the condition. If you want to do the top, you just basically have to use the front. If you want to like display the front or return the front of the linked list, you just have to use the front pointer. If you want to return the back of the back of the linked list, you have to use the back pointer. So everything is clear now. Now, the last thing that I want to show you is the concept of circular linked list. So I'm gonna pause this and then do this. So now we're gonna talk about the concept of circular linked list. In a regular linked list, we have the head pointer that points to the head of the linked list, and the tail of the linked list, it has its pointer part equal to the null pointer, right? To basically show this is gonna be the end of the linked list. In a regular linked list, we only need the head pointer. But now that we are implementing queue, we said that we need to have 2 pointers. So we actually don't need this to be 0 anymore, because we already have a pointer that let us know where the tail of the linked list is. So what we can do, we just like to give more functionality to this linked list, you can make this one point to the head of the linked list. Now, if you want to traverse through the whole linked list, you can just like go back and like it's just gonna be a circular linked list now. Okay, so this is the concept of circular linked list. We have 2 pointers, one pointing to the head, one pointing to the tail, right? And the tail of the linked list, its pointer part, it's pointing to the head of the linked list. Now, if we want to implement a queue using circular linked list, this is like what we had for the linear linked list. Now we're gonna see what needs to be changed. Okay, so here we talk about NQ, right? So this part was the part that we allocated. This is like a new node, and we changed the data and the pointer part of it. Here we checked if this is gonna be the first node that we wanna NQ, the first data that we wanna push, right? If that's the case, we want both front and back to be pointing to the same place. Let me write it down here. So like this is, we have a linked list here, and this is front, this is back. Both of them have to be pointing to the same node, okay? Now, if we have just one node in the linked list, this is both front and the back. If we wanted to make it circular, it just basically, it's kind of weird, but this is how it is. Its pointer part, it's pointing to itself, okay? It's pointer part, not pointing to the same pointer, but pointing to the same node, okay? So this basically means that we can just add one line here. We're saying that rear arrow next, sorry, I should call it back. I called it back. Back arrow next is equal to front. Or I can actually say back, because both of them in this case are pointing to the same thing, but I want to keep it general, so I'm going to do it like this. So back arrow next, this pointer, it's going to point to where this pointer is pointing to. So it's going to point to the same node. Okay? So that's what I need to add to this if block. What else like we have to do? Like here again, we enqueued this number into the linked list, right? And what we had before was something like this, right? Now what do I want to change here? Again, I want to say that back arrow next is equal to the front, so that this is not null anymore. This is going to point to here. This is the only thing I need to change to make the linear linked list and the circular linked list, making back arrow next pointing to where front is pointing to. Okay. Now for the DQ part, what I need to do is basically only looking at this part. If I'm changing the front, right, front is becoming front arrow next. So like, let's say like if we are removing this one, right, front becomes front arrow next. This is the temporary thing that we have to delete. So like my rear is pointing to the, like, sorry, this node's rear, this node's pointer is pointing to the front. Okay, so I want it to be pointing to the new front, not to the old front. So I have to add a line here saying that rear, again the same line, back arrow next is equal to the front. This is going to be removed, and this is going to point to here. Okay, so that's going to change our implementation to a circular linked list. Now this is not in we're deleting T, so this is not there anymore. So this is going to be gone, and our queue becomes these three nodes. Okay, so that's all I wanted to share about the circular linked list. Not much different from the linear one. The only difference is that the last pointer is not null pointer anymore. It's pointing to the head of the linked list. Thank you so much.